Alright, time for another draft physics video presentation. Anyway, alright, so we'll just talk about the basic subject of the difference between kinetic energy and momentum. The fact that momentum is consistent with quantum mechanics in the sense that it's kind of just a quantity, and you're just reducing it to something very simple, which is mass and velocity. And the idea is sort of that mass carries a velocity. So the more mass you have, the more that's like bread, and you're spreading velocity on it, which is the jelly. And the more mass you have, the more bread, okay, the thinner the jelly, the less bread, and you have the same amount of jelly, then it's going to be thicker on the bread, and that's going to be more velocity. So it quantizes nicely, works as an answer. Newton used it to predict things very well. The mechanics works very well. And then it was challenged by some notion of the fact that somehow velocity is much more important than the bread. You know, the jelly is more important than the bread in terms of defining what something can do in the universe. And it sort of breaks the idea of what an exchange is. And an exchange seems to be that you're just basically saying, I can give you bread or I can give you jelly. In doing so, I'm going to give you, if I give you bread, I'm going to give you the jelly that's on it, usually. I don't think there's too many ways to separate those two once you have a velocity. But receiving wise, you can just receive the jelly, the velocity. You can knock it off of one piece of bread and spill it onto another. I'm trying to get to the point of why some of the inverses don't work. It's one thing the difficulty between exchanges that happen between objects that have different masses, and why going from a fast thing to hitting a slow thing versus, well, it's not really a slow thing, right? It's just the masses. If they're the same size, then the exchange is kind of obvious. Whatever is on the bread on one side just slides onto the other piece of bread in terms of the velocity. Just trying to find a metaphor that is suitable to explain the interactions. But anyway, so we'll just talk about this. We'll play this part where Professor Lewin goes on about rockets, and it's probably yes, it's all momentum, and then it's almost just, you can see I have to throw kinetic energy in here, because this is supposed to be one of our facts, so let's throw it in there. But it doesn't make any sense. It doesn't fix anything. It doesn't make it more understandable. Momentum does make it understandable. So let's just go through that part again.
A bullet. So I experience exactly the same force, but in this direction.
So he's again saying the force thing. So he's throwing a tomato, and the idea is that somehow he's experiencing a force by throwing it. And the whole idea of throwing it is you're getting rid of force. You're the one getting rid of something going that way where you're throwing the tomato. So you don't need a counter force because you've already changed your balance by getting rid of something. So I made this argument about so it's relevant to rockets in the sense that there's two parts to a rocket engine. There's two things that are happening. So one part is you're just getting rid of the stuff you have, as you could just say it was water, okay? So you could just say you had a tank full of water up to a certain level, and you got rid of the water going this way. So that means the water you're getting rid of contains a component in this direction, or it can't go in that direction. It doesn't contain the component going this way. And so somehow you're exchanging. You're pushing the water out, but the ship as a whole is keeping this direction. So you didn't give away that direction, to the nozzle. You only gave away this direction through the nozzle. So this direction is still inside of you. You were doing nothing before, and when you were doing nothing, it meant that you had the same amount of this and the same amount of that. Now you can give away some of it. Say you had 90 of these and you had 90 of these. You could give away 10, Now you have 10 extra here, but you only have 80 here, but you gave away some of them. So now you have a bias in a direction. So you don't need an opposite force. You gave away a force. So you have the other opposing force already inside of you. And so now you have this 10% extra, okay, or whatever the percentage would be. And that's, it's a real extra. And so it can be understood just as a quantity. Now the other part, well, that's probably not entirely in the screen, right? No, it's not. Yeah, okay. Yeah, my bad. Anyway, so I just erased the part you didn't see anyway. But it doesn't really matter. So that's one part of what's happening. So just getting rid of the pressure. So you have a pressure tank. You can sort of understand that it has pressure in both directions. And then if you put a hole here, that means you're losing the stuff in this direction, and the other stuff, the stuff bouncing this way is still going that way. So obviously you have a bias in this direction because you got rid of stuff by putting a hole here. You got rid of anything going this way. Anything going this way goes out the hole. So I can put the hole here, and then it's anything going this way. So wherever I put the hole in the tank is the direction of pressure I'll get rid of. I still have all the other directions. I'm just getting rid of the ones going one way. That's sort of the point. So I don't need an opposite reaction, because by making the hole in a certain location, I only got rid of stuff going that way through the hole. All the stuff that didn't go through the hole is still there. Duh. Okay. But the other part of a rocket, obviously, isn't that just that you're getting rid of a fluid in a direction. You're also igniting it. So you have a chemical reaction, where you're taking the fuel plus oxygen, creating bigger molecules and lots of little stuff going very fast. So you're creating byproduct little bits that are going at a very high velocity through the process of the chemical reaction. So the chemical reaction is essentially an explosion. So an explosion is a little different in the sense that you can sort of understand that we can't control the explosion. That is, we can't control, say, two atoms were, this size, and we made them this size. The two little atoms combined are going to take up this much space. So it's taking up space in all directions. It's not taking up space in just one direction. It's taking up space in all directions. So it's pushing on all the other atoms in the, likewise in all directions. So the explosion part is going in both directions. And clearly we're trying to control that by creating mechanisms that will absorb the energy in certain directions and release the energy in certain other directions. So we'll give a free pass. So we don't give a pass to stuff going this way, but we do give an opening for stuff going this way. And then we have a nozzle that's basically saying anything going this way will reflect this way. So we'll get some of the energy in this direction. So by forcing some of it to go this way, we'll lose some percentage of its intensity, but the fact is that we'll try to create the circumstance where it's going this way. It means we'll get the benefit of having a bias in this direction, because we'll force it to go this direction. And to create that bias, something internally has to change something going this way into something going that way, and vice versa, something going this way into that way. And so the rocket, this part, collects a bunch of energy going this way and turns it into energy going that way and that way. And so we're getting the half of the explosion going this way. The atmosphere is getting the half of the explosion going that way, and everything going these other ways, it's trying to convert into those directions. It's trying to convert stuff going this way and this way into stuff going this way and this way. So that's the real, if you just let the fuel out, you're not going anywhere. So this is the part that really makes the thing work, is the fact that you're creating a whole bunch of expansion energy by by creating a chemical process that expands the space the atoms take up. It's making the material, I guess in a sense, less dense. I don't know, the matter less dense. So it's got more empty space in it, and the more empty space in it, and just so it's just, and it does this expansion very quickly. So it goes from this size to this size very quickly. It's very quick movement. So everything it's interacting with ends up getting the very quick movement. So you end up moving a lot of matter very fast in a direction. And you're not getting an opposite reaction. You're getting the other half of that event. Half the event goes that way, and half the event goes that way. So this isn't creating an opposite force. The stuff coming out this way isn't creating an opposite force. The explosions created the opposite force. You're just catching it here. You're putting a sail on this boat to collect the energy, and you're trying to create no sail going that way, so it's free to go. And yeah, good enough. Fix this again. Blah, 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 blah.
And that now is the idea behind a rocket. A rocket is spewing out tomatoes, well, not quite tomatoes, it's spewing out hot gas in this direction, and then the rocket will experience a force in that direction.
All right, so, I'm just saying, he's saying it's going to experience a force in that direction. It's the explosion created that force. It's not going to experience it because there's something going that way. It's going to happen because the atoms are doing this. They're expanding in both directions. And you're catching one direction and ignoring the other direction.
That is the basic concept behind a rocket. And the higher the speed of the gas that it throws out, the higher that velocity, the more kilograms per second it spits out, the higher the MDT.
So this is Newton, basically, okay? So it's just momentum, and you're really just measuring how much jelly, okay? So you put a whole bunch of jelly on the little bits, the small amount of matter, so to speak, and the fact is the other side is doing the opposite. It's taking a big piece of matter, the remaining fuel plus the rocket, and it's gaining the same amount of jelly, same amount of velocity, but it has to spread it over a much more massive object. So it's going to take a while for its velocity to match the velocity of the exhaust because it has so much to move.
The higher will be the force on the rocket, and the force on the rocket is called the thrust of the rocket.
So AB Science doesn't like me using the word thrust to describe what it would be to throw matter out of your ship. So you're in space and you're going to throw stuff out the windows, right? Let's just pretend you have a window you can do that with. You're going to throw stuff out the window. Clearly the velocity has to come from something, some event, and the fact is the event is basically going to have both elements to it. So if you gave away this, you still have this. You gave away what was creating your condition. And if you give some piece of your condition away, you still have the rest of your condition, and there's going to be a difference in what you have because you gave away this, and you still have this inside of you.
So if we have a rocket in space, here's the rocket, and the rocket is spewing out gas with a velocity u, which is fixed relative to the rocket.
All right, so the particles coming out are coming out in all kinds of velocities. So there is no velocity u. There's just an average velocity of the thrust. So there's no point in saying what you're really doing is just saying what's the average. If I took an average of what 1 kilogram was doing of the thrust, or you just get very small, 1/1,000,000th of a gram, 1 atom. What's the average atom speed? So it's not what's the average electron doing, almost you could say, but it's not, the thrust isn't in any way one speed. It's photons. It's lots of different kinds of energy. Lots of different kinds of stuff. Lots of little different bits of atoms. Whole atoms, clumps of atoms, you know, I mean, big pieces, little tiny pieces, and, you know, nuclear bits.
It's the burning of chemical energy. Chemicals are burned, it comes out with a certain speed, and the rocket will then experience a force, which we call the thrust, and that is given by this equation. If you know how many kilograms per second are spewed out, and you know what the velocity is, which I've called u here, this will tell you what the thrust is of that rocket.
Right, so somehow you don't need the kinetic energy formula to get the right answer. So again, where people say, oh, the kinetic momentum doesn't answer the question. Well, yeah, it does. It answers the question.
If we take the case of the Saturn rockets that were used for the landing on the moon. Saturn. For the Saturn rockets, the speed u was about 2.5 kilometers per second. So the gas came out with 2.5 kilometers per second relative to the rocket. And
so it's just the average, based on the kind of fuel they use, what was the average velocity of the particles that come out of the explosion. So depending on whether you use dynamite or gasoline or some other thing, and how much oxygen, you know, how well you oxygenate it, will decide how much of the fuel you actually burn, and therefore how fast the average particle movement is.
rate at which this gas was coming out is phenomenal. 15 tons of material per second.
Right. So the amount of stuff coming out is, you know, significant. So it's a lot. Like if it was water, it's a lot of water, but it's not nearly enough. It doesn't mean anything, even though it's 15 tons moving, you know, out a valve. It doesn't really become significant until you explode it. So until the explosion happens, where you chemically change the gas, that's the part that matters. The idea that you're letting it leave the rocket isn't very important. The fact is that it's leaving by being exploded out of the door. So it's like you push it towards the door with your pressurized tanks. So your pressurized tanks push it towards the door, then it explodes. You know, and the exploding part is the important part.
The NDT.
So I mean, one part is where you're getting rid of your pressure in just one direction out the valve. So you're gaining some power by just letting your crap go out the valve. And the second part comes from an explosion that obviously shoots both ways. So it just should be understood as they're, you know, distinct events.
Is about 15,000 kilograms per second. It's almost unimaginable. And that would give it then a thrust of about 35 million newtons.
See, so it's all perfectly calculable in newtons, which is pressure, you know, weight. So it's all doable, you know, no kinetic energy required.
Which, of course, was higher than the weight of the rocket. Otherwise, the rocket would never go up. An incredible thrust. I have also a nice problem for you in assignment 6 with the Saturn rockets. You'll see these numbers again. These are rounded off.
Very exciting.
So rockets obtain an impulse from their engines. A force acts upon the rocket for a certain amount of time. We call that the burn time. But as they burn...
So again, so the time, so when they do this dt, d blah, 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 he's just saying the burn time. So he's really just saying, you know, as you can convert Newton into saying, when he says change in momentum over change in time, you couldn't just say, well, what's the total time and of the burn and the total change in your momentum. So it really is just saying that force equals momentum. I mean, and obviously if you're just trying to measure an impulse force, it would just be for the time that the event is taking place, that you're burning the fuel and you're shooting all this crap out at all this velocity. Once that stops, the force stops, so that's how you're just calculating it. But it's clearly a clear indication that Newton understood force basically equals momentum, which equals, if he had the word, energy, that they all just equal each other. Very simple.
The fuel, the mass of the rocket, goes down because the fuel leaves. And therefore the acceleration during the burn goes up because the mass goes down. And this makes it somewhat complicated to derive.
Right. So now it's a constantly changing circumstance, because how much mass you have to move is changing. And obviously if you're losing that mass, you're going to lose it in a direction. Okay, so you're keeping the other direction. But yeah, so now how much gravity is affecting you and how much force you have to apply against gravity changes. Now, even though gravity is a constant force and all that kind of stuff, it's a constant force based on your mass. So as your mass changes, the amount of gravity you're absorbing changes. So now it gets, moment to moment, you're changing the equation. So all he's just saying is basically this is just sort of a distraction, because who needs to know this information? A rocket scientist maybe, but I mean, you don't really need to know this.
The velocity change that you get during the burn, during this impulse. It's done in your book, Ohanian. I find that derivation a little bit complicated. I looked in other books and I found one in the book by Kepler on physics, and his derivation, and I will go through that in general terms. I put that on the web for you. It should be there tonight.
Okay, so we're probably best just to skip all the formula crap, so we'll just bounce through it, blah, 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 blah. So, you can use different formulas, but U is basically just the velocity of the material you're getting rid of, and blah, 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 blah. So, go through that, blah, 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 and blah, 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 blah. So let's see where, it gets back to talking theory. All right, so we'll stop here and see what he does.
The rocket equation. Now this is true if there is no external force on the system. It is interesting to include a real launch from Earth. And if you have a real launch from Earth, then the rocket is going up in this direction, but then gravity is exactly in the opposite direction. In other words...
So this equation didn't have gravity included, it just had the consequence of your fuel getting lighter, right, as you're burning it. And so you have less mass to move with your thrust, which is constant, presumably.
Only when you launch vertically from Earth would you have a thrust like this, and you would have mg like this. In that case, this equation has to be adjusted, and then you get ma equals m thrust minus mg. Only if you have a launch from Earth vertically up. Now you have to do a little bit of massaging, and I will leave you with that massaging. A couple of integrals are necessary to convert this into the final velocity of the rocket after the burn.
So you had to massage it to get to here, and then you got to massage it to get it someplace else. Okay, fine, whatever. All right, then he corrects himself on a minor point. I want to just get to where he starts talking about
does not exist.
Other things.
What do you see? That the velocity...
Good grammar and spelling are important, but if you want to write essays that inspire...
equals v initial, we have called that before in 801 v0, that's the initial speed, minus gt. Ha! We had that result during our first lecture. Completely consistent with this equation. If you have no rocket, you get that v equals v0 minus gt, if you throw the object vertically up, and we had a vertical launch.
So again, another way of understanding it is you're never at zero velocity, in the sense that all you're really at is a balanced condition that is relative to the other stuff in the room. But the reality is you are actually moving through space at some velocity, and you have a bias in some directions. But you contain both directions. To say I have zero would be to deny the fact that there's parts of me right now going this way, and there's parts of me going that way, and parts of me going this way, and they're all moving around inside of me all the time. So I have lots of potential energy inside of me in the form of stuff moving in a direction. just that they're both pulling on the same rope, and so the rope doesn't go anywhere until there's a bias.
That looks good. We launch from the Earth, and we now have an initial speed which is 0. The rocket is standing there, and we fire the rocket. T, by the way, is the burn time of the rocket. Let me write that down. T is the burn time. So initial speed is 0. So now, this final velocity, if we want this final velocity to be anything physically meaningful, a positive number, this thing has to come out positive. And you will say, well, how can that be? Because we have a minus sign here, and we have a minus sign there. How can that ever become positive? Well, don't forget that...
So this is just more math stuff. So the logarithm is a negative, blah, 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 and so that makes it negative. I mean, you know, all this just not very good.
That is gone. You have only 10% left when the burn is over. So now we can calculate, if this was a launch from Earth, a vertical launch up, we can calculate how large this term is, take the logarithm of this value, multiply it by minus u, and then we find that the final velocity, the first term is 2300, and the second term, 100 seconds, and this is 10, is minus 1000. So you pay a price for the gravitational field, and so you have about 1.3 kilometers per second is the final speed of that rocket. These are meters per second, and that is in kilometers per second. Now, if there were no gravity, then of course the gain in speed, this difference would be 2300 meters per second.
This is going somewhere. So, I mean, the point is so now he's calculating the actual speed and actual what you get out of your fuel, and now he's going to start throwing the kinetic energy crap in, and it just makes the whole thing silly.
Also, if there is no vertical launch, but if, for instance, the rocket were in orbit around the Earth, here we have the rocket, and going in orbit around the Earth, then of course, even though there is gravity, gravity is now not doing any work. And therefore, if you fire this rocket for 100 seconds, the change in velocity, the tangential change, will also be 2300 meters per second. You cannot say now there is gravity, and therefore we have to take the GT term into account.
Well, you're changing your orbit, so that's not going to exactly work. So if you increase your velocity, you're changing your orbit, which means you're either going away slowly or you're crashing in slowly, depending on which way you change it. So I don't know if that makes much sense.
It would be the same for this equation. If you had an object going in this direction, this minus GT term wouldn't be there either. It's only, of course, when you deal with a vertical motion. It is very important to realize, and very non-intuitive, that when you burn a certain amount of fuel, for a given amount of time, you obtain a fixed change in the velocity. This is fixed for a given amount of fuel.
So he's pointing out how momentum says one thing, okay? That is, you're just going to gain velocity. It's just jelly, okay? The fuel is making jelly. It's making velocity. And that's it. You know, it's always the same. Doesn't matter what you're doing. How fast you're going doesn't matter. How fast you're going previous doesn't matter. It's a certain amount of stuff you got rid of, and you're going to get the opposite reaction. And this is where it sort of just breaks down, because kinetic energy ruins all that.
Change in kinetic energy is not fixed. And I'll give you some numbers so that you can immediately check that for yourself. And it is very non-intuitive. It is in fact a mistake that is made by many physicists.
So when he says non-intuitive, it means it doesn't make sense on its surface. Okay, so, but somehow when you go deeper, it doesn't make any more sense. I mean, it never is made to make sense. So it's non-intuitive, but it's not fixed by some sort of great explanation that explains why it was mirrors and you got the wrong impression. There's no explanation for why it makes any sense to think you got more energy because somehow the fuel could give a damn about what you were doing ahead of time. You know, previously, the explosions could care less what you were doing. Now the explosions don't care.
To think that if you burn the same amount of fuel of the same rocket for the same amount of time, that the increase in kinetic energy is a given. That is not true. It's the change in velocity that is a given. Let's suppose that V final minus V initial is 100 meters per second. That's just a given. I have a rocket, I have a certain amount of fuel, I burn it, and that is my change in velocity. I start off with V initial is 0. So my kinetic energy increase is 1/2 m times 100 squared, which is 10 to the fourth. That's what I got out of this burn. Now I use the very same rocket, the same amount of fuel, the same burn time, so I get again that the final velocity minus the initial velocity is still 100. That's exactly the same. But before the burn, this rocket had an initial velocity of 1,000 meters per second. What is now the gain of kinetic energy? The final velocity is now 1,100. That's non-negotiable, because the rocket changes the momentum, changes the velocity by a fixed amount. So now the gain of kinetic energy, the increase of kinetic energy, equals 1/2 m times 1,100 squared minus 1,000 squared. This is the new velocity, and this was the old one. And this number is 1/2 m times 200,000. This could be in joules, and this is also in joules. This number is 20 times higher. So you see that the change in velocity was exactly the same. The rocket burned the same amount of time, the same amount of fuel, but the kinetic energy increase is way more if the rocket has a higher speed.
Yes, which doesn't make any sense. The fuel can't make more energy, so where did the extra energy come from is the obvious questions. But I mean, the more obvious thing is that, you know, all this equal and opposite reaction force thing he's talking about, all this rocket stuff where you have to shoot the stuff this way to get to that way. And you just argue then, well, how do you explain the gun? How does the gun make 2,000 joules go this way and it only recoils with 4? How come there's only 4 going that way and there's 2,000 going that way? How did it accomplish this task without, like, melting or something? You know, so that's the bullshit part. So anyway, now he's just going to do some fire extinguisher antics. Yeah, a little bicycle with a fire extinguisher. He always has to throw in some stuff that's just a little bit childish. But anyway, whatever. Yeah, so I'll pause. I think that's just that there's no reasonable comments, and so many of these arguments have already been made. I don't know exactly how to reconstruct any of them. Little details do change, right? So I mean, 6 months ago, I didn't realize that, hey, you know, those clay experiments, they don't really prove anything because that was still before they added the 1/2 mv squared. So they also say kinetic energy is wrong. The clay experiments basically are saying, no, kinetic energy theory is wrong because it's mv squared. It's not, there's no 1/2 in front of it. There's no 1/2 mv squared. There's just mv squared. So I'm saying that the spring experiments and the other experiments say kinetic energy is wrong because it doesn't add up. It breaks Newton's laws, blah, blah, blah. But so does the clay experiment. So what experiment does demonstrate kinetic energy to be rational or reasonable or correct? This experiment doesn't seem to work. I mean, you know, the fuel, depending on what I'm doing, the fuel has... you know, 200,000 joules or 1,000. I mean, you know, it's a silly differences in numbers. So anyway, yeah, it's enough. It's probably enough, but I'll pause and think if there's anything else to add and whatever, blah, blah, blah. Tired. All right, back. Anyway, so I just got a link to a Michael Van Briesen video on springs that I'll probably watch the whole series on springs, just to get a little bit more background, see if there's anything interesting in those videos. But anyway, I just noticed something. It was just kind of bizarre. I didn't realize he has 720,000 subscribers. I mean, just 750,000 subscribers. And his new videos only get, you know, less than 1,000 views. I mean, it's an incredible disconnect, you know, between the view numbers. You know, even if you go back a month, I mean, it's like they're still barely getting over 1,000. Yeah, you know, I mean, so obviously all the other subscribers like me, you know, just find the videos when they're not on subjects you give a shit about, they're just so ignorable. Who cares, blah, blah, blah. And so nobody watches the videos as they're, you know, still not over 1,000. A month-old video, still not over 1,000. Yet he has some videos that are, you know, hundreds of thousands of views. So it's just so uneven. It's just very strange. I mean, it's just really, you know, it's just, the numbers just mean that like, nobody, none of these people who are subscribed, I don't even understand it in the sense that they're still subscribed, but they don't ever watch any of them, barely. So, they just show up in the subscription box and they just nope. It's of interest to so tiny a percentage, the new videos, the subjects. But I like I said, some of it I understand because I have to admit that I would only click 1 in 100 of the videos just because the subjects aren't very. There's too many subjects. I guess that's the thing, right? Then you just can't be interested in most of them. Something like that, anyway. So, just curious, just an interesting fact thrown in for the hell of it. So anyway, let's just get the hell out of here and say it's a video. Yeah, I mean, I've already made all the arguments, just waiting for the counter arguments, waiting for somebody to answer the questions in the description of the video. There's too many, all these paradoxes haven't been explained. The kinetic energy formula doesn't fix anything, it just breaks things. Why? Why are you people so aggressive in defending something that has no experimental evidence defending it? I mean, zero. Pretty much. I mean, none. There's just none experimental evidence demonstrating this to be the correct way of viewing energy. Showing this getting collecting the joules of energy produced by the bullet versus the joules of energy produced by the gun. No, there's just no evidence. Anyway, so till the next time, and such, and so forth and whatnot. Blah 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 blah.